One of the reasons why logistic regression models are so widely used in practice is because one can use an odds ratio to interpret the effect that an explanatory variable has on the response variable. To see this, let's consider a logistic regression model that has just simply one variable in it. We'll just simply call it x. Notice how we're modeling the log of an odds of a success. So we have log of odds of success on the left side, and then we have this linear predictor, beta 0 plus beta 1 times x, on the right side. Now, if I were to apply the exponential function to both sides of this model, I have 1 over 1 minus pi. The odds of a success are equal to the exponential function evaluated at beta 0 plus beta 1 times x. We can write this odds of a success more compactly as, let's say, just odds, and then to emphasize that we're referring to x, the odds at x. So for example, if we were to go back to the place kicking data example, we would have, let's say, the odds for a particular distance where I could just plug in the distance value, maybe a 30-yard place kick. I could just plug that in there and get the odds of a success at that distance. Now, what if we increase our x explanatory variable by c units? So again, going back to the place kicking data, suppose I were to increase x by 10 yards. Let's say to go from a 30-yard place kick to a 40-yard place kick. Then we can write this in a general form as, now I have an x plus c there. So notice also in this little subscript for emphasis, I have x plus c there as well. So now we have two odds. We have an odds at x, we have an odds at x plus c. What do we do when we have two odds? Well, we simply take the ratio to form an odds ratio. So the odds at x plus c divided by the odds of x. Now look what happens when we replace then this model formulation with in there with respect to those odds. The beta zeros cancel out. The beta 1 times x here cancels out there as well. And so that all you're left with is the exponential function evaluated at c times beta 1. Notice that x has totally disappeared. This is a very, very, very important aspect with using odds ratios to interpret the effect that x has on the response variable. Meaning it doesn't matter, going back to the place kicking data example, it doesn't matter if you're talking about a 30-yard place kick compared to a 40-yard place kick, or a 40-yard place kick compared to a 50, or a 55-yard place kick compared to a 65-yard place kick. It doesn't matter what the actual numerical value of x is. The only thing that matters is the c. What is the unit increase that you're looking at? In that last example, 10 yards. That's the only thing that matters. This then is one of the reasons why, again, logistic regression models are so widely used, is because now I have this nice interpretation of my explanatory variable and its effect on the response variable. So I did this little derivation here, you could say, for a model that has only one explanatory variable. Suppose you have a model with, let's say, p explanatory variables, and you're interested in the you're interested in the rth explanatory variable, just to be general. Make sure you can go through this same kind of derivation on your own with that little bit larger model. In the end, you just have more things that cancel out. So how do we interpret then this corresponding odds ratio that we get for this simple model that has only one explanatory variable in it? Well, one possible interpretation is to do something like this. The odds of success are the exponential function evaluated at c times beta sub 1 times as large for a c unit increase in x. Another correct interpretation would be the odds of a success changed by that odds ratio times for every C unit increase in X. This just kind of emphasizes that we're talking about any C unit, like a 10-yard increase. So these interpretations are a little bit different from what we saw before when we had a 2x2 contingency table. The reason being is because now we're talking about these C unit increases, but it's the same, essentially the same concepts that we saw earlier. So this C unit increase in X, excuse me, just a more convenient way of saying, let's say if group 1 was X plus C and group 2 was X, from what we were talking about before. Now, before, again, we had a 2x2 contingency table, meaning we had these two groups, group 1 and group 2. Well, what if in our particular situation we had X representing a 2-level categorical explanatory variable? Now, the way that would be typically represented in a logistic regression model, or actually any regression models, you have one level that would have a coding of 0 and another level that would have a coding of 1 associated with it, such as like the change variable in the place-kicking data set. Well, what happens to the odds ratio in this particular setting? So I could find the odds at X is equal to 0. Again, assume that we only have one explanatory variable. And notice what happens. This beta 1 times 0 becomes 0, and I have the exponential function evaluated at beta 0. The odds at X equal 1, look what happens. I plug a 1 in there. Now I'm left with the exponential function at beta 0 plus beta 1. So then what I can do is find a ratio of those two odds. And essentially the result ends up being exactly the same as if C was equal to 1. So here's my odds ratio. The beta zeros cancel out, and I'm left with the exponential function evaluated at beta 1 itself. In this particular setting, since I only have 2 levels for my explanatory variable, then I can go back to the same interpretation that we saw previously in chapter 1, such as the odds of success are the exponential function evaluated at beta 1 times as large for X equal 1 than for X equals 0. Okay. So what about, though, an estimated odds ratio? Because after all, we're going to be taking a sample, and using the sample, eventually we want to make inferences back to the population value. What we've been finding here essentially is the population value. So to find then the corresponding estimated odds ratio, all we do is we put a hat on top of the corresponding beta. In this particular case, I have this written in terms of a more general model that has, let's say, P explanatory variables in it, and we're just looking at the Rth explanatory variable. And since this is an estimated odds ratio, now I need to put a hat on top of OR. This ends up being the maximum likelihood estimate. Okay, let's talk about making inferences then to the population version of our odds ratio. So we're going to be talking about doing confidence intervals. Now, similar to what we saw in chapter 1, where we needed to find a confidence interval for a particular quantity, then make a little transformation of it to get it into an odds ratio scale, we need to do the same thing here. We're going to first talk about Wald confidence intervals because they're the easiest to construct. And so if I wanted to do, first of all, let's say in suppose I wanted to do a confidence interval for just beta 1 itself, and suppose again I have this simple logistic regression model with only one explanatory variable. So to do a Wald interval for beta 1, all I would do is take beta hat 1 plus or minus quantile from the standard normal distribution. Let me run out of space there. And then I could go to my estimated covariance matrix, find the estimated variance of beta hat 1, take the square root of it, and there is my corresponding confidence interval. Okay, now remember that an OR is equal to the exponential function evaluated at C times beta 1. So how about we find a confidence interval now for C times beta 1? So as you might expect, I can put a C there. I can put a C inside there as well. Now, in another stat course, you've learned something like this, where, well, if you've had a mathematical statistics course, that the variance of a constant A times a random variable Y is equal to A squared times the variance of Y. So because of that, then my estimated variance of C times beta hat 1, which I have right here, ends up being C squared times the estimated variance of beta hat 1. That C squared, notice that's going to be right there. That C squared is just a constant, can be factored out, and ends up, because of the square root, being just C itself. So here's my confidence interval for C times beta 1. Now, to form a confidence interval for my odds ratio, I just apply the exponential function transformation to this, and here's my confidence interval for the odds ratio. Simple way to find this. Now, another interval that unfortunately is a little bit more complex to find, but it performs better in terms of true confidence levels, is the profile likelihood ratio interval. The name likelihood ratio, we've seen that before. Remember, that's our lambda statistic that we've seen, the ratio of two likelihood functions evaluated at corresponding maximum likelihood estimates, where the numerator has some restrictions to it. Now, this particular interval is found the following way. Let's say I wanted to do a hypothesis test in our simple model that we have that has only one explanatory variable in it. Suppose I wanted to do this hypothesis test. We've seen that we could use the -2 log lambda statistic to do this test. And then we know for a large sample, if we think of this as a random variable, this has a chi-square 1 distribution to it. 1 because there's only one parameter that's being tested in the null hypothesis. And so we can compare this value here to a chi-square, a quantile from a chi-square 1 distribution. So we would say don't reject if a chi-square 1 quantile, the 1 minus alpha quantile, if we say do not reject if -2 log lambda in terms of the actual calculated value is less than that quantile. And so what one could do then, so that would be my hypothesis test. And we've talked about inverting a test before, and we could do something very similar here to find a confidence interval. Suppose instead of, let's say, testing is beta 1 is equal to 0, suppose I just put in general some number there, we'll just call it D, and I have these hypotheses instead. Now, to invert the tests, what one would basically need to do is find all possible values of D such that my test statistic is always less than that quantile from the chi-square distribution. That would give me a range of possible values of D. The smallest number in that range is the lower limit of my interval for beta 1. The largest number is the upper bound or upper limit for my confidence interval. Now, this process here is actually a little bit more complicated of inverting than what we've seen before. The reason being is because our model doesn't just have beta 1 in it, but it has beta 0 in it too. And so because of that, if you remember this lambda here, the numerator is the maximum possible value of the likelihood function, subject to the null hypothesis being true. But since I have this beta 1 there, I need to find the maximum likelihood estimate for beta 1 subject to I need to find the maximum likelihood estimate for beta 0 subject to beta 1 is restricted based upon the null hypothesis. And so that's what makes this a little bit more complicated. And because I also have to worry about beta 0, that's why this isn't just referred to as a likelihood ratio interval, but rather what's called a profile likelihood ratio interval. Okay, so that gives you some background here. And so in the end, this is how the interval is found. I have my negative 2 log lambda statistic. The denominator is the maximum possible value of the likelihood function evaluated at the MLEs for the unrestricted model. The numerator, though, is the maximum possible value of my likelihood function subject to this kind of restriction where I put in a particular value of beta 1, maybe like 0.1, maybe 0.5, maybe 10. I put that in there, then try to find the maximum possible value of that likelihood function under that restriction so that I can estimate beta 0. And so what we're looking for is in all possible values of beta 1 such that this stuff on the left side is less than the 1 minus alpha quantile from a chi-square 1 distribution. That's a profile likelihood ratio interval for beta 1 itself. Now, going back to what we were seeing before, I need an interval for c times beta 1 and then use the exponential function with that to find an interval for the odds ratio. And that's what we end up doing. So that I get my interval for beta 1, let's call the lower limit lower for the lack of a better name, the upper limit upper for the lack of a better name. I take it times c, and then I apply the exponential function transformation with it. Okay. Now, if you like a little bit more maybe explanation regarding this profile likelihood ratio interval, what I've done actually in my program is show you like an ad hoc approach that one could use to find this likelihood ratio interval that's different from how we will end up doing it in the end, where this ad hoc approach is just simply there for educational purposes. And basically what I do is I try a bunch of values of beta 1 and I try to find the maximum possible value of that likelihood function, allowing myself to actually find an MLE for beta 0 subject to a particular value of what beta 1 could be. I find my negative 2 log lambda statistic. I look at, well, what values of this beta 1 actually fall, have this inequality satisfied, and that's how I get my interval for beta 1. So unless otherwise stated in class, you're not responsible for that. It's just meant there to give you an additional explanation of how to find this profile likelihood ratio interval. So now that I have my interval, how do I interpret it? Well, I use a similar interpretation that we've seen before. Now with 1 minus alpha times 100% confidence, the odds of a success are between whatever that lower limit is to the upper limit times its large for a c unit increase in x. Okay, some comments then before we get to an example. Sometimes with odds ratios, it's nice to always have a value that's greater than 1. So at times you might need to invert the odds ratio. So if you have an odds ratio of 0.5, well, you might want to invert it to be 2 so that you can interpret it that way. When that does, of course, when that happens, you need to change your interpretation correspondingly. Something that's very important for practical applications. Choose a value of c, this constant increase in our explanatory variable. Choose a value of c that makes sense relative to the explanatory variable of interest. So if x is measured on a numerical scale that for some reason is only between 0.1 and 0.2, it would not make sense in that scenario to use a c equal to 1. Similarly, if x is measured on a numerical scale that tends to be between, let's say, 0 and 1,000, very often it's not going to be of interest to use a c equal to 1. The reason why I emphasize this is that sometimes it can be easy to be, let's say, lazy and just always use c equal 1 all the time. But in many problems, a value of c equal 1 will not make sense relative to that data. And for those of you who are taking my class, I will take off points in a graded project or test if an appropriate value of C is not chosen. Now, when there is more than one explanatory variable in your model, you need to add a little bit something extra to your interpretation, similar to what you would do for a normal linear regression model when you would interpret that. So let's go back to one of our interpretations that we've seen before. So, for example, the odds of a success are whatever the odds ratio is, times as large for a C unit increase in, how about we say X of R, if we have a model that has P explanatory variables in it. For a C unit increase in X of R, holding all of the other explanatory variables constant. Okay? This means that, okay, you're just focusing on that particular explanatory variable. The other explanatory variables cannot change in your model if this same interpretation is holding. So, for example, let's say if you had one explanatory variable called x1, you looked at a C increase in it. You had another explanatory variable, let's call it x2, and for some reason you decided to simultaneously increase that by, let's say, D units. Well, now that's going to totally change what your odds ratio ends up being. So, look at the derivation of the odds ratio to actually see that if you were to change two variables at the same time, you're going to get a different odds ratio than what I had presented. Okay, let's get back to where we were. Okay, these note 4 and note 5 here, or comment 4 and comment 5, correspond to something that we're going to be doing a little bit later in chapter 2 when we have more complicated models. So for example, let's say I have a quadratic term in my model. So not just, let's say, x, you have maybe x squared. As you might expect, then that's going to change your interpretation. So I put this additional stuff here for note 4 and note 5 here to say, okay, we're just going to talk about simple models here where we have like a variable like distance or change in it. But once we get more complicated models where maybe we have a quadratic term, maybe what's called an interaction term, or a categorical explanatory variable with more than 2 levels, things will change a little bit. So hold on until we get to those later subsections of the notes to deal with those kinds of variables. Okay, so let's take a look at an example. We're going to get back to the place kicking example once again where we only have distance in our model. To find then the corresponding estimated odds ratio corresponding to distance, let me jump on over here to 10. What we can do, let's say if C was equal to 1, I use the exponential function, and then I grab out my beta hat 1 from my mod.fit $ coefficients, where mod.fit is where we store the results from the GLM function. Just to show you that, there's beta hat 1. Use the exponential function with that. Here's my odds ratio, 0.89. Now, this odds ratio, at least for football fans, is not very informative. What this says is that, let's say the place kick was increased in distance by just 1 yard. For football fans, one knows that that's not very meaningful in terms of football. What would be more meaningful, though, is let's say we look at a 10-yard decrease in distance. So note that C doesn't have to be a positive number. You just simply need to change your corresponding interpretation from before when I said a C unit increase. We could look at a C unit decrease instead. So in football, there's something called a first down in football. In order to get a first down, you have to gain 10 yards. In this particular case, the place kick would need to be 10 yards shorter. And so relative to that, the game of football, a C of -10 makes very, 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 makes a lot of sense. I'll just say it that way. So if I say the exponential function -10 times beta hat, I get 3.16. So let me come back over here to my Word document here. So what's then the interpretation then? Well, the estimated odds of success are 3.16 times as large for a 10-yard decrease in the distance of the place kick. Notice here how I put estimated because this is based upon our data itself. We are getting what's often referred to as a point estimate for the population version of the odds ratio. One could also say that the estimated odds of success change by 3.16 times for every 10-yard decrease in the distance of the place kick. Again, notice this means I'm talking about a decrease from 35 yards to 25 yards. I'm talking about a decrease of 50 yards to 40 yards or 65 yards to 55 yards. It doesn't matter where I start in that decrease. Only the decrease itself is what's important in this interpretation with this odds ratio. Now, let's find now the confidence interval because we want to make inferences to the population of all place kicks, not necessarily those place kicks that were done in this one season where this data was collected. And so I need to find this confidence interval. So to find the confidence interval, excuse me, to find a profile likelihood ratio interval, first what we can do, we can use a function called confint to do the calculation for us to find a confidence interval for beta 1 itself. Confint is actually a generic function in R. So I say confint object equal the results from my GLM function I put in there, mod.fit. Parm corresponds to, well, which regression parameter are we trying to find a confidence interval for? I want to find the one corresponding to the distance variable in my data set. So this distance this name here has to match what is actually displayed in the results for mod.fit. Then level equal 0.95, meaning I want a 95% interval. I'm going to put the results into an object called beta.ci. Oops. Okay, hold on. I accidentally hit the wrong button here. Okay, so here's my corresponding confidence interval. The lower bound is negative 0.13. The upper bound is about negative 0.1. That's my profile likelihood ratio interval again for beta 1. We want to transform this now to a profile likelihood ratio interval for the odds ratio itself. So what I need to do is take the lower bound and the upper bound times negative 10. Now I have an interval for C times beta 1. To do this on the odds ratio, to do this for an odds ratio, then I use the exponential function with this. And I get 3.73 to 2.69. Now note, the way that this is displayed is it puts the larger number first. It puts the smaller number second. And that's not how we write out confidence intervals. We always, for a range, we put the smaller number first, the larger number second. So to make a simple change here, to change that order, I use the REV function for reverse. And now here's my confidence interval. Notice R puts some labels with this that don't necessarily make sense now in this particular case. So to remove those labels, I can use the adds.numeric function, which says, okay, just simply treat this as numerical values. I don't care about any labels that are there. So that's how I do my profile likelihood ratio interval. It's not too difficult to do. Once we get into more complicated forms of odds ratios, though, then it will become more difficult, and stay tuned for that. So how do I interpret this then? Well, with 95% confidence, the odds of a success are between 2.69 and 3.74 times as large for a 10-yard decrease in the distance of the place kick. Notice I do not have the word estimated right before odds because I'm no longer talking about estimated value. I'm talking about a confidence interval for the actual true value, the population value. Now also notice that the interval is entirely above 1. Why is that important? Well, remember, an odds ratio that's equal to 1 says the numerator is exactly the same as the denominator. Here we have shown that indeed the whole interval is above 1, indicating that we have shown that there is a distance effect, meaning that distance does affect the odds of a success. Also that correspondingly, distance affects then the probability of success as well. We have shown that. Also, something that I think I failed to mention before is that notice that this interval is above 1 here. So what that says is for a 10-yard decrease, my odds of success increase for making the place kick. And this corresponds to what football fans would expect, and that is that the closer or the shorter the distance for the place kick, the higher the probability of success, or equivalently higher the odds of success. Now, profile likelihood ratio intervals are the most desirable to use, but you could do a Wald interval here. And so to do that, we can use a particular method function R called confident.default. And we use a very similar syntax. We use similar code once we get the interval. And we notice that, or you can notice that this interval is very similar to what we had before for the profile likelihood ratio interval. The reason is simply because we have a large sample size. On your own, you can take a look at that. How would you calculate the Wald interval without necessarily using without using confident.default? And I give the corresponding code that one can do that. And the reason why I do that is because it helps emphasize some of the stuff that we talked about before with like how to extract a particular variance from a covariance matrix. And lastly, for those who are really interested in the computational aspects of a profile likelihood ratio interval, especially if you're a statistics major, this is good. Otherwise, you're not necessarily responsible for this on any kind of graded work, but if you're interested in the computational aspects, I show how to find the profile likelihood ratio interval using an iterative numerical procedure that is outside of confident. I use a function called uniroot to find what that interval is. This is in my corresponding program. Okay, so then this concludes then our section on odds ratios relative to logistic regression models.